Okay then, hello and welcome for today's session. So today we're going to talk about the feedback amplifiers. So before starting a feedback amplifier, so let us revise about the previous tutorial. So in the previous tutorial we talked about the transistor amplifiers, transistor amplification, and we have solved few examples, and we also discussed about the transistor can be used as a switch, and we have solved few examples related to that. So now quickly we have the two examples related to the transistor switching. We will talk that and then we will jump on to the feedback amplifiers. So now here there is an example. It's just basic analysis of transistor can be used to switch on and off the light. Now for example, if we have the circuit here which is in a common emitter configuration which is connected in this way, where I have my resistor here and it is connected to the collector through the LED. So this is an LED here and the emitter terminal is grounded, and here I am applying my V in. So this is the resistor RB, this is RC, and this is VCC. So to analyze this circuit, it's very simple. Now for example, here we are applying the input in a form of a square wave or a square pulses. So this represents the 0 volts and this may represent say 5 volts or 10 volts or anything like that. So it is same as the switch that we have discussed in the previous tutorial. So when the input voltage is 0, what happens? The circuit remains to be open, then the LED remains to be off. So what is the main criteria for LED to turn on? For LED to turn on, its anode terminal. So this is an anode terminal and this we call it as a cathode terminal. So this anode terminal should be connected to the positive voltage. So it might be plus 5 volts or plus 10 volts through a current limiting resistor. I have not written a current limiting resistor. And the other end, the cathode should be connected to ground. If this transistor is like open switch, means if it is open like this, then it means this ground part is disconnected. If this ground part is disconnected, it means that the LED is not on, it remains to be in the off state. To make this LED on, so then what happens next? The input is high here, it means we are applying the base with the 5 volts and the transistor is on. When the transistor is on, then it completes the path through the transistor to the ground, that the LED will be turned on. So this is the basic analysis of this simple circuit. So we can use this kind of simple circuit to make the transistor on and off. So based on the applying the voltage or current to the base terminal. So now let us solve one simple example related to this. So here question is given that, so an LED requires, so here the question is that the LED requires 30 milliamperes of current. So it requires a 30 milliamperes of current to emit the sufficient light. So this is the requirement. So now let us rewrite the same circuit. So if you rewrite the same circuit here, so the emitter terminal here, and this is my VN and this is my RB, and here I have the RC resistor and this is my LED connected. Yes, and this is the VCC connected here. So this is the RC resistor and this is an LED. So LED we represent like symbolically like this. It means it is emitting light outwards. And here the beta value which is given is that the beta value is 50 and this RB resistance is given as 3.3 kilo ohms, and this is RC is 270 ohms and VCC is equal to 9 volts. So these are the given requirements. So now we have to determine the amplitude of the square wave input voltage, so that we have to determine. So what is the V in? So we have to determine what is the V in this case, the amplitude of it, which is necessary to make sure that the transistor is saturated. and it is suggested to use the double the IB value, means IB minimum, double the IB minimum value to ensure that the transistor in the saturation region, and it is told to assume that VCE minimum, the VCE minimum is equal to 0.3 volts. So VCE minimum is equal to 0.3 volts. So now if we use our previous derived equations, that is IC saturation, so if we try to calculate the saturation current, collector current, then it is given as VCC minus VCE VCE minimum whole divided by RC. So then if you substitute the values here, so this is 9 minus 0.3 divided by this RC is nothing but the 270 ohms. So when we simplify this, we will get the current somewhere here, that is 32.2 milliamperes. 32.2 milliamperes, so which is very much greater than the 30 milliamperes. What is the required current? So the current which is flowing here through this entire path, that is the current IC. So the question, it is given that the minimum current for LED to glow is 30 milliamperes, and what is the current that we are maintaining here? So the current which is maintained is 32.2 milliamperes. So it means now the LED is on, so there is no doubt the LED will turn on when we give the appropriate inputs. So now we have to calculate what is the input voltage required. To calculate the input voltage, we will first calculate the minimum base current required. So the minimum base current that can be calculated as IB minimum, which is equal to, we know this is equal to the IC saturation. We can calculate with this formula, that is IC saturation by beta value, because beta is given, so we'll use this formula. So let us substitute this here. So now it is 32.2 milliampere whole divided by the beta value, so that is 50. So now if that is done, so then we will get our value, the IB value as 644 microamperes. So 644 microamperes I will get here. So then next, it is suggested to take the double the value of IB minimum to make sure that the transistor remains to be in the saturation. So if I want to take the double the value, then it is just multiplied this value by 2 times. So 644 microamperes into 2 will result in that 1288 microamperes. So we can also call this as a 1.2 milliamperes as well. So now we know the equation for the base current, that we can also write this as V in IB is equal to V in minus VBE. If you apply the KVL across the input, and that is divided by RB. So then here we have to find the V in, we have the IB, everything. Then we will rewrite this equation. Then if I rewrite this equation, then it is V in is equal to, so what do we get here is that we have RB into IB plus VBE. So this is the equation which we'll get if we rewrite this. So now if we substitute all the values for RB, IB and VBE, so then, so let us substitute this. So this is 3.3 kilo ohms here. So it is 3.3 kilo ohms into, this is 1288 microamperes plus, it is, we know that for silicon transistor VB value will be equal to 0.7 volts. So when we add up all these values, so probably we should get the value as 4.96 volts. So now what is the input voltage required to turn on this, the magnitude of this? So now we are talking about the magnitude. So it is approximately equal to 5 volts. Now the magnitude for transistor to keep it off, so that's give it 0 to make it on. So we need to give the voltage of 4.96 volts, which is approximately equal to 5 volts. So this is about the transistor can be used to switch on and off the LED. So that's it for this. If If you have any queries with respect to this example, you can ask quickly. Otherwise, we can switch back to the feedback amplifiers. So now, if you don't have any queries, then we'll talk about the feedback amplifiers. So an amplifier is nothing. We all know that amplifier is a circuit where if you give a weak signal, then the output signal is a magnified or boosted version of the input signal. Why do we use that? For example, it might be used in many places. When you're transmitting a signal after a certain distance, what happens? The signal gets weak. It will get weak in terms of its power, in terms of its magnitude. So we need to boost the power and its magnitude. So then we go for the amplifiers. So how actually these amplifiers are working? So for the transistor to work as an amplifier, or if we talk about the amplifier circuit, there is something called a feedback. There are two types of feedback. So let me type it here. There are two types of feedback. So in that, the first one is positive feedback, and second is negative feedback. So now let us understand what is the feedback first, then we will talk about what is the positive and negative feedback. So to understand that, we'll just write one symbolic representation or the block diagram kind of thing here. So this is our circuit, some circuit which is producing a gain. So it can be an op-amp or it can be a transistor. So then you can see this like this. So we have some input voltage or input signal. So now here we are applying the input signal here. So we are applying the input signal here, and that input signal has to be, whether it depends, it will get magnified or it will get reduced or whatever. So output signal. So this is the output signal. So it has certain gain. So it has certain gain which is amplifying. Along with that, so what we will do is that this output we will take and feed to this feedback network. So this we call it as a feedback network or feedback circuit. So the feedback voltage is added or subtracted with this input. So that we call it as VI. So now here if I write in terms of mathematical equation, then VI is equal to V in plus or minus VF. So VF is the feedback voltage which is get added up or get subtracted up with the input signal. So now here we have talked about the two types of feedback, positive feedback and negative feedback. So positive feedback means if we add this voltage, the output voltage back to the input, so this we will call it as a positive feedback. And if we subtract the output voltage with the input voltage, then we call it as negative feedback. So now for an amplifier, which is the better one? So whether we should go for the positive feedback or should we go for the negative feedback? That is the question. So now if we look into these aspects of this, then if you go with the positive feedback, it means if we add V in with VF, the output oscillations keep on increasing. It means definitely we're going to achieve the magnitude, but the problem is that here the noises will also get amplified. So we don't want an amplifier also to boost the noise along with the signal. So there is a problem with this positive feedback amplifier. So for amplifiers, we'll always go for negative feedback amplifier, where we are subtracting the output with the input with certain portion, and then it is again magnified to certain level because we have this gain A here. So then it's not an issue. So whereas for oscillators is the circuits where we generate the oscillations, desired frequency oscillations. So there we will go for the positive feedback because there we are not applying any input. So by it is self-generated oscillation circuits. So there we will give the positive feedbacks. So that is why it will generate the oscillations. So now we'll talk about, let's see a little bit the basics of this feedback amplifier. So now if I talk about the particularly with respect to amplifiers, so if we are talking about the negative feedback amplifier, so it means I have write here minus. So it means it subtracts, Vf is subtracting with Vn. So now if you look into a few mathematical equation aspects with respect to gain and all, so generally we will define the gain A is nothing but the V out by Vi. So now we are not taking V in, because if we just see from this part, so this is the amplifier basically. So here this is my output and this is the input. Now what is input? Input is nothing but V in. This is the difference of these two inputs, V in. This is the A, we can call this as the base amplifier. So this we can call this as the basic amplifier. So this we can call it as a basic amplifier. So it's not proper, so let me write. So we call it as the basic amplifier, right? So then the overall feedback, including feedback if we consider, then the overall gain if we consider, that is defined as Vf, so that is V naught by V in. So here we are considering the overall gain of the amplifier with feedback. So this is without feedback. So here the base amplifier without feedback, and this is overall amplifier, overall gain of amplifier with feedback. So now beta is the feedback factor. So here the beta is the feedback. Please do not get confused with this beta with the transistor current amplification factor beta. So that is different and this is different. So this is, we are now in the different topic. So this beta here, it represents as the feedback factor. So this is defines the feedback factor. So then we have, that is A is equal to V naught by Vi, and Vf, sorry, then we have Af is equal to V naught by Vn, then V naught is equal to A into Vi if you write this equation, and if you look into Vi, so Vi is nothing but the difference of V minus Vf, this we know it, and this can also be written from this equation that Vn minus Vf is nothing but beta into V naught. So if you see here, so what is Vf? Vf is nothing but beta into this V naught. So V naught which is here, so it is multiplied with that. So we will get the Vf as beta into V naught. So then if I substitute for V naught, so if you substitute this equation here, then what do we get here is that so V naught is equals A of this entire thing, that is V in minus beta into, sorry, it is V naught. So then we will there are two V naught terms, so I'll send it to the left hand side. Then if I take the V naught common here, so I'll get to 1 plus beta here equal to A into V in. So then if I write this, then the overall feedback, if you see here, then V naught we can substitute here in this case, then AF is equal to, so what is V naught? So V naught is nothing but, I can write this as A into V in by 1 plus beta 1 plus beta into, what do I get here, V in. So what happens here, V in get cancelled. So what did I did, I just substituted for V naught. So V naught, if you rewrite in this equation, so I'll get V naught is equal to A into V in by 1 plus beta. So V in get cancelled. Then finally it is the overall feedback is given as the feedback of the amplifier plus by divided by 1 plus beta into A. Beta into, sorry, I have forgot one term here, so this is into A. So it is beta into A. Sorry, this A is not here. So this A is not here. This is here, because when we multiply here and take onto the left side, so then we will get this. So now this is perfect. So let me rewrite this equation properly. So then I have the overall gain AF is given by A, gain of the amplifier, divided by 1 plus beta into A. So 1 plus beta into A. So this is the equation for this. So now this negative feedback amplifier has certain properties and it has certain advantage. So let us talk about that. So if you talk about the properties of negative feedback amplifier, then the first property is that it has reduction. It has a reduction in gain. Why is that reduction in gain? Because if you look into the above equation, the overall gain, if you look into the overall gain, it is not just A multiplied with something else, it is A dividing. So there is the feedback network is dividing the value of the gain. So we have the gain is little bit reduced compared to the positive feedback. So that is what it means. Then the desensitize the gain, then it has reduced non-linear distortion. So that's what, as I said, the distortion will be less, and reduces the effect of noise. Then it control the input and output resistances and extend the bandwidth of the amplifier. So these are the properties of negative feedback. Now if you look into the advantages of the negative feedback amplifier, then we have that stabilized gain, then it has higher input impedance, then lower output impedance, then increased bandwidth, then reduction in noise, and so on. So these are the properties and advantages of negative feedback. So now we will talk a little bit on there's feedback concepts, not much in detail because all results in the same thing. There are quite a few examples as well. So there are four types of negative feedback. One is the voltage series feedback, voltage shunt feedback, current shunt feedback, and current series feedback. So these are the different types of feedback. So we'll just take one and then we'll quickly jump on to the example, because this is not that important with respect to our syllabus here. So I'll just give you the intuition, the types of negative feedback. The first one is voltage series feedback, and second is voltage shunt feedback. The next one is the current shunt feedback and current series feedback. So now we'll take the one of these and we'll see the how the connection looks like. So we'll take the voltage series feedback. From the voltage series feedback, if you see here, so this is my input. So here I'm connecting to so this is the amplifier A. This is the amplifier A, and this is the resistance RL. This is represent nothing but the V out, and now we have the one more box here, that is beta, and then it is feedback network, the feedback network here. The types of feedback which we have talked about is that, so this is my VI here, so this is positive, negative, this is positive, negative, and sorry, this is VF, feedback voltage, and this is VI, which we have talked just before, the equations. And the impedance at this point we call it as ZI, and the impedance at this point we call it as ZIF, the overall input impedance, and here the output impedance is just Z0, and this is the overall output impedance, that is ZOF, and this is the VF. This is positive and this is negative, so feedback network. So now when we talked about the voltage series feedback, it means in the series with this we have taken the output back to the input. If it is shunt, means we have to connect like this in parallel in the output. So likewise for current shunt and current feedback. So I will not talk much about this. So I will take one simple example here. So if you look into the example here, it is given an amplifier has a bandwidth of 200 kilohertz and the voltage gain of 1000. So here first thing which we have to determine is what will be the new bandwidth new bandwidth and gain if 5% of the negative feedback is employed, means when we applied employed. And second question is, what is the gain bandwidth product? What is the gain bandwidth product with and without feedback? And third is, what must be the feedback factor required for bandwidth of 1 megahertz? 1 megahertz. So what is the bandwidth required for 1 megahertz? So this is our question here. So it is given there is a bandwidth. So we have not talked about the bandwidth. Anyway, I'll give the straight away equation for that. So the gain A is given as the gain of the amplifier is equal to 1000, and the bandwidth here, it is, we are talking about, it is of 200 kilohertz. So now the first question is that, so what will be the new bandwidth if the 5% negative feedback is employed? So now 5% negative feedback, in the sense, now the value of this beta is equal to 5%. So the value of beta is equal to 5%, then what is the denominator factor that we have written? So the denominator, the feedback VF, is given by, it is 1 plus beta into A. So that is the this thing. So now we will compute this. It's actually beta into V naught. So if you look into this previous equations here, so if I come back here, so it's basically, if you look into generally, what is a feedback network? So feedback network is nothing but that is beta into V naught. So beta into V naught is, we can write in this way, in a better way if you write, so then V naught of 1 plus beta into A. So we have just added one more factor, that's it, that is A. So now if we try to find this, so now substitute all the values for this, we have the gain and everything, so then we will get the value as equal to 1. So the bandwidth equation for this is very simple. So bandwidth with feedback is given by bandwidth of this feedback. So it is given by 1 plus the feedback factor. So it is 1, the overall feedback. So it is 1 plus beta into A. So this is nothing but it is 200 kilohertz into 51, which will give the bandwidth of 10.2 megahertz. 10.2 megahertz. This is what we will get here. So then the second thing which we need to find is that what is the gain bandwidth for the product with and without feedback. So if you look into the gain product without feedback, so if we consider without feedback, so then it is just A into bandwidth. Just concentrate on the equation. So it is A into the bandwidth which is given. So it is 1000 into the 200 kilohertz which is given there. So then we have a bandwidth of 200 megahertz. So it is 200 megahertz. And the gain width, this is the gain without feedback. Now the gain with feedback is given by, that is AF is equal to A by 1 plus beta into A. So substitute all the values here. So when we substitute here, we know it is 1000. This is 51 plus 1. You can just see here it is, yeah, it is 51. So then we will get this value as 19.6. So this is the gain factor, and the gain bandwidth for this case is given by, the gain bandwidth is given by, that is AF into, you multiply this bandwidth here, which is given in the feedback bandwidth. So then we have this 19.6, and the feedback bandwidth that we got here is 10.2 megahertz. 10.2 megahertz. We will get this as, say, 200 megahertz. And the third one is that, what is the third one? We must, what must be the feedback factor required for bandwidth of 1 megahertz? So a bandwidth of 1 megahertz with feedback. So with feedback we need to have the bandwidth of 1 megahertz. So what should be the feedback factor, that is beta, we need to calculate. So to calculate beta here, it's a reverse process. So then we will use the equation, that is bandwidth with feedback is given as the bandwidth, that is the bandwidth of 1 plus beta into A. So this was the equation that we used. Now we rearrange this equation. So when we rearrange and calculate the equation, then we'll get the beta value is equal to 0.004. So this is the value of beta which we need to get a bandwidth of 1 megahertz. So that's it for today's session. So thank you. In the next session, we're going to talk about the oscillators. Goodbye.